Hello everyone, welcome to my talk. My name is Xiaoyu Zhang from Xi'an Jiaotong University, and I'm here to present AutoTrainer, an automatic DNN training problem detection and repair system. This work was done in collaboration with Jian Zhai and Shixing Ma from Rutgers University, Chao Shen from Xi'an Jiaotong University. Recent advances in deep learning have made it possible to benefit users in many fields: machine translation, virtual assistants. These convenient tools are inseparable from deep learning. However, deep learning still faces challenges. In order to obtain better learning effect and be competent in more complex tasks, DNN models continuously become larger and the training also become more and more onerous. Misfortune never comes singly. The onerous training may still fail and tend to non-convergence. There are many reasons for the training failure, such as the gradient explosion, buggy models. Most of them are training problems. However, existing training tools like TensorBoard and Manifold only provide limited support for training. They can track and visualize the training history, gradient, and weights, but they cannot detect the problem. Users still need to check the problems manually after training. In fact, debugging training problems is not easy work. Because of the random initializer and other random operations used in training, this problem occurs randomly, which makes the prediction difficult. Even worse, once the problem occurs, the training process will be affected and even turn to non-convergence. To confirm the randomness and the seriousness of training problems, we conduct repeated experiments. In the first one, we built a DNN model with 34 layers and 650,000 parameters on a mixed dataset and found that training problems occur randomly. This model uses ReLU activation and the Glorot initializer. We treat this model 50 epochs with Adam optimizer and repeat for 100 runs. Notice that this repeated training uses the same training scripts and the same environment. The pie chart shows that one training problem called dying ReLU occurs in 80 runs, but not in the remaining 20 runs. The average accuracy of 80 buggy runs is 11.34%, and the other runs accuracy obtained 85.34%, which is significantly higher than the buggy runs. In addition, training problems also occur randomly during training. For another training problem called oscillating loss, we conduct an experiment similarly to the previous one and train 100 repeated runs with the same training scripts. This time we build a 20 layers model with 410,000 parameters. The activation function and initializer we use are the same to the previous one. The distribution of the stage when the problem occurs is shown in the pie chart on this slide. We can see that the problem occurs separately in the training. It occurs in the first 10 epochs in 50 runs, and the rest of the problem occurs in other stage is 9, 8, and 4. There are even 29 runs trained normally until the end. The accuracy of each stage is 90.36%, 89.82%. 86.89%, 85.99%, and 90.47%, which exists significant difference between them. To solve the training problems in a timely and automatic manner, we set two designing goals. The first one is to detect the training problem actively during training, and the second one is to repair a buggy model automatically. Based on these goals, we design AutoTrainer, which consists the problem detection module and the automatic repair module. The whole system starts by training a model and uses a training recognizer to analyze the recorded data from the training monitor. For the found training problems, the system uses solution scheduler to try to repair, and finally outputs a repaired model or a failure report. The system is shown on this slide. The broken line shows the data flow and the full line indicates the control flow. The detection part mainly contains the training monitor, recorded data, and the problem recognizer. The training monitor is a timely monitor for the training process and records the static data and the runtime data. The static data includes the model definition, such as the activation functions and optimization details, like the learning rate. The runtime data is collected in the training process, and it includes the training logs and other necessary variables like the weight. Based on the recorded data, the problem recognizer analyzes and checks for the bio-training problems regularly. These problems include the vanishing gradient and the exploding gradient, which have plagued people for decades. In the vanishing gradient problem, due to the chain rule in backward propagation, the gradient can be vanishingly small, especially for the layers that are close to the input layer. Consequently, the training will end up with high loss value and low accuracy. Similar to the vanishing gradient, in the exploding gradient problem, the gradient can grow exponentially as it is propagated backwards. This also leads to unexpected large value or not a number value. As a result, the training will also end up with a high loss value. In addition, the problem recognizer also detects the die-in-relu, oscillating loss, and the slow convergence. Die-in-relu happens when loss of neurons in a model receive non-positive input. When loss value go up and down frequently during training, it may be considered as oscillating loss problem. And for the slow convergence problem, it happens when high loss value decreases so slow that no significant improvement has been made in training. To solve the above problems, Solution Scheduler, which is the main part of the automatic repair module, has prepared some built-in solutions. The main role of the scheduler is to pick one solution to fix the problem and restart the training procedure. Here is one example. When a die-in-relu model has been passed to the scheduler will pick one solution, like the IDBN layer in this figure, to try to solve the problem and retrain the model. If this try fails, the scheduler will try other solutions. If the problem is solved by any solutions, the repaired model will be output to users. To evaluate our system, we aim to answer 3 research questions shown on this slide. We performed our experiments on 6 popular datasets, and in total we collect 495 models. Most of them are from GitHub, existing paper, and experts. In our experiment, AutoTrainer detects 316 problems and repairs 309 problems with a ratio of 97.78%. For the models that AutoTrainer failed to repair, we found that they are too hard to be repaired, even for the manually try. The accuracy has been improved 47.08% in average. Here are 3 real cases on MIS dataset and Cepha dataset. The orange curve is the repaired accuracy curve, and the blue curve shows the original accuracy. From these figures, we can see that the AutoTrainer does improve the training a lot. The RQ2 results show that the AutoTrainer can detect and repair problems efficiently. For the buggy model, AutoTrainer takes 1.19 times more training time on average and very limited memory overhead. Notice that most of this time overhead is used to retrain the model. Solution Scheduler only uses less than 1% of the total time overhead. Comparing with the current strategies, which requires lots of manual operation and time consuming, the cost of AutoTrainer is quite low. Here is a real die-in-relu case mentioned in RQ1. The following bar charts show that AutoTrainer uses 0.58 times more training time and obtain 9 times higher accuracy than the original model, but their memory costs are nearly same. The last RQ is to explain how we choose the parameters in our system, and this slide shows the default value we finally choose. All the details can be found in our paper. In conclusion, we present AutoTrainer, a monitoring and auto-repairing system for training problems. We summarize and formalize definitions for the symptoms of 5 training problems, and the AutoTrainer is the first approach to detect and repair training problems automatically during training. Our evaluation results also show that AutoTrainer can detect and repair training problems efficiently and effectively. So much for my presentation. Thank you for watching. Now I'm opening for questions.
Hello again, those that have joined the first presentation. We are in the and this time Xiao Yu will answer the questions about the AutoTrainer that he proposed. The questions come through the chat, so please don't hesitate to make the questions, and the author will answer them as soon as they show up. Please, can you go ahead and answer the first question we have?
Okay. I'm going to answer this question now. Did you see that certain architecture are more prone to have? Okay. In our experiment, the RNN models. How to talk about this? We obtained our model from the researchers and the online community. So we don't know that. So also we have not calculated which kinds of architecture are more prone to have certain kinds of problem, because all these models are obtained from the online community and existing papers and researchers. So we have not certain computation about this problem. But I think RNN are very probable to have vanishing gradient problem. I think this may be connected to the RNN activation. Maybe RNN architecture use more sigmoid or tangent edge in their training. So if they have long, if their depths becoming larger, and maybe the vanishing gradient problem will be easy to occur. But we didn't calculate about this in our experiment.
While we receive more questions, I would like to make one. I was concerned, okay, that during that your tool is fixing the problems during the training, but it looks to me that this procedure may induce some kind of overfitting in the network. So it answers very well to the training set, but maybe not to real data sets. Have you studied that? Do you have an idea of the overfitting is possible or not?
The overfitting problem, I think this is more, overfitting is more like a phenomenon or a symptom of a kinds of training problems. I think it is hard to focus this kind of problem on a single point, like what a certain reason to cause this. So in AutoTrainer, we do not try to solve AutoTrainer this huge kind of problem in this version. But I think we will focus on more kinds of training problems like overfitting or underfitting, and we will try. This will be our future work. We will improve AutoTrainer later in our future.
Shang Wen is making a question in the chat. So it says how to get the Oracle information during evaluation. That is, whether a model is really buggy.
Okay, the Oracle information we do in our experiment. We do this. We first start to parallel training to each model and make sure that the only difference between them is whether training with AutoTrainer, and they will have the same training script and the same optimization, same environment. And then we analyze their two training results. If this problem do have the training problems in the same training optimization and the same environment, it will occur in the training without AutoTrainer, and that's how we know whether they have training problems. When you fix the model, do you start training from scratch or continue training?
Way my questions.
Okay. When we fix the model, we will use our solutions to modify the models or the model architecture, like add BN layers, or we maybe just modify the training scripts, like change adjust their learning rate, and then we will restart the training, not continue the training, because when we fix the model, maybe we add the DNN layers or add the activation functions. This model is not the same, so we choose to restart the training, but not the continue training.
Christopher is also making a question.
How would your solution work with architecture like GAN and would the generator and okay, we have not tried our solutions on GAN, and in current version we have tried on the CNN model and the DNN model with pure dense layer, and RNN models with simple RNN and LSTM layer. So I think we in the future we will try these solutions on more architecture. Like maybe we will try this on GAN or other like the transformer. This will be our future work. We will try more and try to solve more training problems.
Claudio is making another question and some comments.
Different to solve different problems. Have you been significant?
If you need clarification, simply say so, and I'm sure Claudio will write a very short clarification for you.
Well, I think we have a lot of built-in solutions to solve different kinds of problems, and some kind in specific architecture like DNN layers or the thin architecture, but others may be performance better in RNN. So this difference existing or do existing. Over these layers, I think this difference do existing. So we have implement a lot of solutions for one kind of training problem. That is maybe solution one fails in this architecture, or in we can use solution two to retrain the model and try to solve this problem. That's how we do this. I think in the future we will implement more built-in solutions to try to solve more kinds of training problems and solve the problems in different architecture. This will be our future work. We will try to build a more complete system based on our AutoTrainer. AutoTrainer now is a demo version, and you can get it. It is open source in our repository. You can get it, and you can have a try. We have some demo kits in our repository.
Going to have 50 seconds before we move to the breakout room. Just a very quick question, and remember that when the time is over, you have the option to join the discussion room and talk to the author more in depth for longer time. Okay, so one very quick question: if you want to put this in practice in industry, what are the next steps?
I beg your pardon. I'm sorry.
Yeah, if you want to apply your proposal in industry, what are the next steps that you need to take, or people need to take?
I think in the next step we will try to make the solutions how to say this, more practice, and try to append more problems which we can solve by AutoTrainer.
We go to the discussion.
Hello.